Tonight, we're going to talk about something that shouldn't be possible to discuss. An object that has a name, a definition, a clear physical description, and yet does not exist. Not because it's fictional, not because the physics is wrong, but because the universe itself hasn't been around long enough to make one. It's called a black dwarf, and it is the final fate of an entire category of dead stars. Trillions of them are out there right now, slowly dying, slowly fading, slowly cooling toward a state that none of them have reached. Not a single one. Anywhere. In the entire observable universe. And by the time you understand why, you're going to see the future of the cosmos in a completely different way. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To understand what a black dwarf is, you first need to understand what it comes from. And what it comes from is a white dwarf. A white dwarf is not a living star, it's a dead one. But it's a dead star that still glows. And that distinction, that strange lingering glow from something that has already died, is the entire foundation of what we're going to explore tonight. Because a black dwarf is simply what happens when that glow finally stops. When the last heat drains away, when the last photon escapes, when the corpse of a star finally goes completely cold and completely dark. But that process takes so long that the universe hasn't been around long enough for it to happen even once. Let's start at the beginning. Not the beginning of the universe, but the beginning of the end for a star like our sun. Stars spend most of their lives in a state of balance. Deep in their cores, nuclear fusion is taking place. Hydrogen atoms are being crushed together under immense pressure and temperature, fusing into helium and releasing enormous amounts of energy in the process. This energy pushes outward in the form of radiation pressure. At the same time, gravity is pulling everything inward, trying to collapse the star under its own weight. These two forces, radiation pushing out and gravity pulling in, reach an equilibrium. The star holds its shape. It shines steadily. It's stable. Our sun has been doing this for about 4.5 billion years, and will continue for roughly another 5 billion. During this entire time, the sun is slowly converting hydrogen into helium in its core. It's burning through its fuel at a rate of about 600 million tons of hydrogen every single second. That sounds like a lot, and it is, but the sun is so massive that it can sustain this rate for billions of years without running out. But it will run out. Eventually. Every star that fuses hydrogen in its core will one day exhaust that supply. And when it does, everything changes. When a star like the sun runs out of hydrogen in its core, the core contracts. Without the outward push of fusion energy to hold it up, gravity wins and the core begins to shrink. As the core contracts, it heats up. The layers of hydrogen surrounding the core, which were previously too cool to fuse, now find themselves under greater pressure and higher temperatures. Hydrogen fusion ignites in a shell around the now inert helium core. This shell burning produces more energy than the core fusion did, and the outer layers of the star begin to expand. The star swells enormously. It becomes a red giant. When our sun reaches this stage, roughly 5 billion years from now, it will expand dramatically. Its outer edge will push past the orbit of Mercury. It will swallow Venus. It may even reach the orbit of Earth. The sun's surface will cool as it expands, turning from its current yellowish white to a deep red. But the total energy output will actually increase because the surface area has grown so enormously. A red giant is a star in crisis. Its core is contracting while its envelope is expanding. The structure is unstable. For a star around the mass of the Sun, the helium that has been accumulating in the core will eventually reach temperatures high enough to begin fusing. Helium nuclei will fuse into carbon and oxygen. This is a new source of energy, but it doesn't last nearly as long as hydrogen fusion did. The helium in the core is consumed relatively quickly over tens of millions of years rather than billions. And here is where things get critical. A star with the mass of our Sun is not massive enough to fuse carbon. Carbon fusion requires temperatures and pressures that only occur in the cores of much more massive stars at least 8 times the mass of the Sun. For a star like ours, once the helium in the core is exhausted, that's it. There's no next stage, no new fuel to burn. The core is now made of carbon and oxygen, but it will never get hot enough to fuse those elements. Fusion is over. The star's energy source is gone. What happens next is dramatic. The dying star begins to shed its outer layers. It pulses. Its outer envelope becomes unstable and is gradually expelled into space, forming an expanding shell of gas and dust. This expanding shell is called a planetary nebula, though the name is misleading. It has nothing to do with planets. The name dates back to the 18th century when early telescopes showed these objects as round, greenish disks that resembled the planet Uranus. The name stuck even after astronomers figured out what they really were. What's left behind after the outer layers are blown away is the exposed core of the star. A dense, hot, incredibly compact object, roughly the size of Earth, but containing about half the mass of the Sun. This is the white dwarf. Let me help you picture this because the density involved is staggering. A white dwarf has a mass comparable to the Sun packed into a volume comparable to Earth. The Sun's diameter is about 864,000 miles. Earth's diameter is about 7,926 miles. You're taking all the mass of something 864,000 miles across and compressing it into something under 8,000 miles across. The result is extraordinarily dense matter. A teaspoon of white dwarf material would weigh roughly 5 to 15 tons, depending on the white dwarf's exact composition and how close to the center you scooped from. If you placed that teaspoon on a household scale, the scale would be crushed. If you placed it on the ground, it might sink into the earth beneath it, depending on the surface. The density of a white dwarf is about 1 million times the density of water. These are numbers that don't connect to anything in everyday experience. You've never held something that weighs 5 tons in a teaspoon. Your brain doesn't have a reference point for that. But it's real. White dwarfs are real objects observed throughout the galaxy. There are billions of them in the Milky Way alone. Now, here's the question that defines everything about the white dwarf's future. What holds it up? If fusion has stopped, if there's no outward radiation pressure from nuclear reactions, why doesn't the white dwarf just collapse under its own gravity? After all, gravity is still there. It never went away. The mass of the white dwarf is still pulling inward, trying to compress the object further. Something must be resisting that compression. And something is. It's called electron degeneracy pressure. This is a quantum mechanical effect that arises from the Pauli exclusion principle. Like, in simple terms, the Pauli exclusion principle says that no 2 electrons can occupy the exact same quantum state simultaneously. When matter is compressed to the densities found inside a white dwarf, the electrons are squeezed so tightly together that they essentially run out of room. They're packed as closely as physics allows. And at that point, they push back, not because of any chemical bond, not because of electromagnetic repulsion in the usual sense, but because the laws of quantum mechanics literally forbid them from being squeezed any further. This quantum pressure is what holds the white dwarf up against gravity. It's not generated by heat or fusion or any ongoing process. It just exists as a consequence of how matter behaves at extreme densities. And because it doesn't depend on temperature, the white dwarf can cool down as much as it wants and still remain structurally stable. It won't collapse. It will just sit there, held up by the fundamental nature of electrons, slowly radiating away its heat into the darkness of space. But there's a limit. Electron degeneracy pressure is powerful, but it's not infinitely powerful. There's a maximum mass that a white dwarf can have before gravity overwhelms even the quantum pressure of its electrons. This limit was calculated in the early 1930s by the Indian astrophysicist Subramanian Chandrasekhar, and it bears his name. The Chandrasekhar limit is approximately 1.4 times the mass of the Sun. Any white dwarf with a mass below this limit is stable. The electron degeneracy pressure holds it up permanently. It doesn't matter how cold the white dwarf gets. It doesn't matter how many trillions of years pass. As long as the mass stays below 1.4 solar masses, the white dwarf will remain intact. It will cool, it will crystallize, it will eventually become a black dwarf, but it will never collapse. The electrons won't allow it. But if a white dwarf were to gain mass, if it were accreting material from a companion star in a binary system, for instance, and if its total mass exceeded the Chandrasekhar limit, then electron degeneracy pressure would fail. The electrons would be forced into such high energy states that they would combine with protons to form neutrons. The entire structure would collapse catastrophically. Depending on the circumstances, this could trigger a thermonuclear explosion that destroys the white dwarf entirely, which is what happens in a type 1a supernova, or the core could collapse into a neutron star supported by a different kind of quantum pressure, neutron degeneracy pressure at even more extreme densities. The Chandrasekhar limit matters for the black dwarf story because it tells us that every white dwarf that will one day become a black dwarf must have a mass below 1.4 solar masses. This isn't a narrow window. It actually encompasses the vast majority of all stars that have ever existed or ever will exist. Stars with initial masses up to about 8 solar masses end their lives as white dwarfs, shedding enough mass during the red giant phase that their cores fall comfortably below the Chandrasekhar limit. Stars more massive than about 8 solar masses take a different path entirely. They can fuse carbon, then neon, then oxygen, then silicon, all the way up to iron. And when iron accumulates in their cores, fusion can no longer generate energy. The core collapses and the star explodes as a core collapse supernova, leaving behind a neutron star or a black hole, not a white dwarf. So the stars that produce white dwarfs, and therefore the stars whose remnants will one day become black dwarfs, are the ones below about 8 solar masses. That's roughly 95 to 97% of all stars in the universe. The overwhelming majority. Almost every star you can see in the night sky will end its life as a white dwarf. Almost every star will eventually become a black dwarf. The exceptions, the ones massive enough to explode as supernovae and leave behind neutron stars or black holes, are the minority. They get more attention because their deaths are dramatic. But the quiet majority, the stars that simply fade away, those are the ones whose future we're exploring tonight. This is the crucial point. A white dwarf has no energy source. Fusion has stopped. There are no nuclear reactions occurring in its core. No new energy is being generated. The white dwarf is simply hot. It's hot because it used to be the core of a star. The core of a star is extraordinarily hot. Temperatures in the core of a star like the Sun reach about 27 million degrees Fahrenheit. When that core is exposed as a white dwarf, it starts out incredibly hot. A newly formed white dwarf can have a surface temperature exceeding 180,000 degrees Fahrenheit. That's roughly 18 times hotter than the surface of the Sun right now. It glows brilliantly. It's blue-white, searingly bright, radiating enormous amounts of energy. But all of that energy is residual. It's leftover heat from the star's former life. Think of a white dwarf like a coal pulled from a fire. When you first pull it out, it's glowing red or orange. It's radiating heat intensely. But the fire is gone. There's no flame, no combustion, no new energy being added. The coal can only cool. It radiates its stored heat into the surrounding air, and as it does, it glows less and less brightly. Eventually, after enough time, the coal goes completely dark. It's still there. The matter hasn't gone anywhere. But it's cold. It's black. It no longer emits light or noticeable heat. A white dwarf does the same thing, except it does it on a timescale so vast that it defies human comprehension. When a white dwarf first forms, it's among the hottest objects in the galaxy for its size. It radiates energy furiously from its surface. Photons stream away in every direction, carrying thermal energy into space. And as each photon leaves, the white dwarf gets just slightly cooler, just slightly dimmer. The process is relentless, and it never stops. There's no mechanism to reheat the white dwarf. No new fusion can ignite. No external energy source is pumping heat in. The white dwarf can only lose energy. It can never gain it back. So it cools, year after year, century after century, millennium after millennium. The surface temperature drops. The color changes. From blue-white to white. From white to yellowish. From yellowish to orange. From orange to red. Each stage takes longer than the last because as the white dwarf cools, it radiates less energy per second, which means the rate of cooling itself slows down. It's like a bathtub draining. At first, the water rushes out because the water level is high and the pressure is strong. But as the water level drops, the pressure decreases and the water drains more slowly. Near the end, the last little bit of water takes an absurdly long time to trickle out. A white dwarf does the same thing with heat. The first stage of cooling, going from 100,000 degrees to 10,000 degrees, might take 1 billion years or so. The next stage, going from 10,000 degrees down to a few thousand degrees, takes several billion years more. But getting from a few thousand degrees down to essentially zero, down to the point where the white dwarf emits no detectable radiation at all, takes not billions of years but trillions, potentially tens of trillions of years, maybe longer. The numbers become so large that they lose connection to anything familiar. And this is where the black dwarf enters the picture. A black dwarf is the theoretical end state of a white dwarf's cooling process. It's what you get when a white dwarf has radiated away all of its residual thermal energy. When its temperature has dropped so close to absolute zero that it no longer emits significant light or heat. a black dwarf wouldn't glow. It wouldn't shine. It wouldn't be warm. It would be a dark, cold, fantastically dense sphere, roughly the size of Earth, but with the mass of a star, drifting through space, invisible, silent. A crystalline remnant of something that burned brilliantly for billions of years, and then spent trillions more slowly going dark. The term itself is descriptive. White dwarfs are called white because they glow with thermal radiation. As they cool, they become less white and more red. Eventually they would become so cool that they would emit no visible light at all. They would be dark, black, hence black dwarf. The name is a projection, a prediction, a label for something the universe is slowly, inevitably building but has not yet completed. And here is the fact that makes this entire topic so extraordinary. Not a single black dwarf exists anywhere in the entire observable universe. Not one. The universe is approximately 13.8 billion years old. That's a long time by any human measure. It's about 3 times the age of the Earth. It's about 60 times longer than the age of the dinosaurs. It's long enough for stars to be born, live, and die many times over. And yet, 13.8 billion years is not long enough for even the oldest white dwarf to finish cooling. The oldest white dwarfs in the Milky Way are estimated to be about 10 to 11 billion years old. They've been cooling for an extraordinarily long time by our standards. And they're still glowing. They're dim. Some of the oldest ones have surface temperatures of only about 5,000 to 7,000 degrees Fahrenheit. That's cooler than the surface of the sun, cooler than many stars, but still thousands of degrees above absolute zero. They're still radiating energy, still emitting photons, still visibly glowing, even if faintly. They have not completed even a fraction of the journey toward becoming black dwarfs. Let me say that again because it's important. The oldest white dwarfs in existence have been cooling for over 10 billion years, and they are not even close to becoming black dwarfs. Not halfway there, not a quarter of the way. They've barely started. The cooling process to reach a true black dwarf state would take somewhere in the range of a quadrillion years or more. That's A1, followed by 15 zeros. Some estimates put it even longer, at 10 to the power of 15 to 10 to the power of 25 years, depending on the mass of the white dwarf and the composition of its atmosphere. These are timescales that are almost offensive in their enormity. The universe would need to be roughly 100 to 1,000 times older than it currently is before the first black dwarfs could form. Some calculations suggest it could be much longer than that. The universe at 13.8 billion years old is a newborn compared to the timescales required. This means that black dwarfs are not observed objects. They're not something astronomers have detected with telescopes. You can't point a telescope at the sky and find one because there are none to find. They exist only in the mathematics, only in the physics, only in the projections of what will happen given enough time. They are the future, not the present. They're something the universe is building incredibly slowly, 1 degree of cooling at a time, across timescales that make the current age of the cosmos look like an eye blink. This raises an interesting question about how we think about scientific knowledge. We're accustomed to astronomy being an observational science. Astronomers see something, measure it, and then explain it. Planets were observed before they were understood. Stars were seen before nuclear fusion was discovered. Galaxies were photographed before anyone knew what they were. But black dwarfs are different. They were predicted before they could possibly be observed. The physics tells us they must eventually exist. The cooling process is real and well understood. White dwarfs are real and well observed. The mathematics of thermal radiation and heat loss are solid. Everything points to the same conclusion. Given enough time, every white dwarf in the universe will eventually cool to the point where it no longer emits meaningful radiation. That final state is the black dwarf. But the universe hasn't cooperated. Time hasn't passed in sufficient quantities. So we're left in a remarkable position. We know what a black dwarf is. We know how it forms. We can describe its properties in detail. And yet, no one has ever seen one because none exist yet. It's like knowing exactly what a fruit will look like when it's ripe. Having studied the tree and the soil and the weather patterns, but the fruit hasn't finished growing. It's still on the branch, still green, still years away from ripeness. Except in this case, it's not years, it's trillions of years. Every white dwarf currently in existence is somewhere on this cooling curve. Some are young and hot, freshly exposed cores still blazing at temperatures exceeding 100,000 degrees. Some are middle-aged, having cooled for a few billion years, still clearly visible but dimmer than they once were. Some are ancient, 10 billion years old or more, faint and reddish, among the dimmest objects in the galaxy. But all of them, every single one, are still on the curve, still cooling, still radiating, still warm enough to glow. None of them have reached the bottom. None of them are black dwarfs. And none of them will be for an unimaginable length of time. So when you hear the term black dwarf, understand what it really refers to. It's not a type of object you can go out and find. It's not something that exists in any catalog or database of astronomical objects. It's a prediction, a mathematically certain future state. It's the answer to the question, what happens to a white dwarf if you wait long enough? And the answer is, it goes dark. Completely, utterly dark. But the waiting part is the problem. Because the universe hasn't waited long enough. Not by a factor of 100. Not by a factor of 1,000. The universe is so young compared to the timescale required that calling it young almost understates the point. Imagine you planted a seed and someone told you the tree would take 1,000,000 years to grow, and you've been watching the seed for about 1 day. That's approximately the ratio we're dealing with. The universe has existed for 1 cosmic day out of the 1,000,000-year growing season required for a black dwarf to form. This is where the story of the black dwarf truly begins. Not with the object itself, because the object doesn't exist yet, but with the process. The agonizingly slow, relentless, unstoppable process of cooling. A process governed by the laws of thermodynamics, the properties of degenerate matter, and the insulating effects of thin stellar atmospheres. A process that started the moment the first white dwarfs formed billions of years ago, and that will continue for trillions of years into the future. A process that has no off switch, no pause button, and no way to reverse. Every white dwarf in the universe is on this journey. Every single one is slowly becoming a black dwarf. The destination is certain. Only the arrival time is in question. And that arrival time is so far in the future that it belongs to a chapter of cosmic history that hasn't begun yet. A chapter that won't begin for timescales that make everything in human experience, everything in the entire current age of the universe, look like a rounding error. That is what a black dwarf is. The final state of a dead star's cooling. A dark, cold, impossibly dense remnant that will one day exist in enormous numbers throughout every galaxy in the universe. But not yet. not for a very, very long time. And understanding why it takes so long, understanding the physics of that cooling process, is where this story goes next. Because the slowness isn't accidental, it isn't arbitrary. It's built into the fundamental nature of how heat escapes from an object, as dense and as strange as a white dwarf. And once you understand that process, you'll understand why the universe has to be patient on a scale that almost nothing else in physics demands. Now that you understand what a white dwarf is and where a black dwarf sits at the end of that cooling journey, we need to talk about the journey itself. Because the cooling of a white dwarf is not a simple process. It's not like watching an ember fade over the course of an evening. It's governed by physics that conspire at every stage to slow things down, to stretch the process out, to make each step take longer than the one before it. The universe isn't just waiting for white dwarfs to cool. It's watching them cool in a way that gets slower and slower and slower as time goes on. And once you understand why, you'll see that the formation of a black dwarf isn't just delayed. It's delayed by design. The physics of how heat escapes from a white dwarf is built to resist the very thing that would create a black dwarf. Let's start with the basics of how any hot object cools. Every object that has a temperature above absolute zero emits thermal radiation. This is electromagnetic radiation, photons, that carry energy away from the object's surface. The hotter the object, the more radiation it emits. This relationship is described by something called the Stefan-Boltzmann law, which tells us that the total energy radiated by an object per second is proportional to the fourth power of its surface temperature. That phrase, fourth power, is important. It means that if you double the temperature of an object, it doesn't radiate twice as much energy. It radiates 16 times as much. 2 to the fourth power is 16. If you triple the temperature, it radiates 81 times as much. 3 to the fourth is 81. This relationship has a critical consequence for cooling. When a white dwarf is very hot, say 100,000 degrees at its surface, it's radiating an enormous amount of energy every second. Photons are streaming away from its surface, carrying huge quantities of thermal energy into space. The white dwarf is losing heat rapidly. It's cooling fast. But as it cools, as its temperature drops, the rate of energy loss drops dramatically. A white dwarf at 50,000 degrees radiates only 1/16 as much energy as one at 100,000 degrees. A white dwarf at 25,000 degrees radiates only 1/256 as much. The relationship is steep. Every time the temperature drops, the rate of cooling drops much faster. This creates a cooling curve that decelerates relentlessly. The white dwarf cools quickly at first, then more slowly, then even more slowly, then barely at all. Think about it this way. Imagine you're draining a swimming pool through a hole in the bottom. When the pool is full, the water pressure is high and the water rushes out quickly. But as the water level drops, the pressure decreases and the flow slows down. Near the end, when there's just a thin layer of water at the bottom, the trickle is agonizingly slow. You could drain the first 90% of the pool in a few hours, but the last 10% might take all day. Now imagine a version of that pool where the drain hole also gets smaller as the water level drops. That's closer to what's happening with a white dwarf. Not only does the driving force decrease as the temperature drops, but the very mechanism of heat loss becomes less efficient. The photons emitted at lower temperatures carry less energy individually. The peak of the thermal radiation shifts to longer wavelengths, from ultraviolet to visible light, to infrared to microwave. Each photon carries less energy away. The total number of photons emitted also decreases. Everything conspires to make the cooling slower and slower. Let me walk you through the numbers because the timescales involved are where this story becomes truly staggering. A newly formed white dwarf might have a surface temperature of around 100,000 to 180,000 degrees Fahrenheit. At these temperatures, it's blazing hot, emitting intense ultraviolet radiation. Over the first few 100 million years, the white dwarf cools relatively rapidly. Its surface temperature might drop to around 36,000 degrees Fahrenheit. That's still extraordinarily hot by any human standard. Hotter than the surface of most stars. But the white dwarf has already lost a significant fraction of its initial thermal energy. Over the next billion years or so, it cools further. The surface temperature drops to maybe 18,000 degrees, then to around 9,000 degrees over the next few billion years. At this point, the white dwarf looks like a dim version of a normal star. It's glowing white or yellowish, still clearly emitting visible light, but far less luminous than it once was. After about 5 to 6 billion years of cooling, a typical white dwarf might have a surface temperature of around 7,000 to 8,000 degrees. That's similar to the surface temperature of our sun right now. The white dwarf is still quite warm, still glowing, still clearly visible to a telescope, but it's been cooling for longer than the Earth has existed, and it's still thousands of degrees above absolute zero. Now here's where the deceleration really kicks in. Getting from 8,000 degrees down to 4,000 degrees takes longer than getting from 100,000 degrees down to 8,000 degrees. The process is slowing down that dramatically. After 10 billion years of cooling, some white dwarfs have surface temperatures around 5,000 to 7,000 degrees Fahrenheit. These are the oldest, coldest white dwarfs we've actually observed. They're dim and reddish, barely glowing, emitting most of their radiation in the infrared rather than visible light. They're among the faintest objects in the galaxy, but they're still warm, still radiating, still thousands of degrees above absolute zero, and they've been cooling for nearly as long as the universe has existed. From here, the timescales become almost absurd. Getting from 4,000 degrees down to 1,000 degrees might take another 50 billion years. Getting from 1,000 degrees down to 100 degrees might take trillions of years. Getting from 100 degrees down to 10 degrees might take tens of trillions of years. And getting from 10 degrees down to essentially zero, to the point where the white dwarf is in thermal equilibrium with the cosmic microwave background radiation, which currently sits at about minus 454 degrees Fahrenheit, or about 2.7 Kelvin. That might take quadrillions of years or more. Each step is longer than the last. Each degree of cooling requires more time than the one before. The cooling curve is asymptotic. It approaches zero temperature but never quite reaches it. And the approach gets slower and slower without limit. But the Stefan-Boltzmann law and the basic physics of thermal radiation are only part of the story. There are additional factors that make the cooling even slower than you might expect from thermal radiation alone. And the first of these is crystallization. As a white dwarf cools, something remarkable happens inside it. Remember, the interior of a typical white dwarf is made primarily of carbon and oxygen. These elements exist in a state called a degenerate plasma. At very high temperatures, the carbon and oxygen nuclei are free to move around. suspended in a sea of degenerate electrons. The interior behaves like a very dense liquid, but as the temperature drops, the nuclei slow down, their thermal motion decreases. At some point, the electrostatic repulsion between the positively charged nuclei, combined with their reduced kinetic energy, causes them to settle into fixed positions relative to each other. They form a lattice, a regular, repeating three-dimensional arrangement of atoms. In other words, the interior of the white dwarf begins to crystallize. This was predicted theoretically decades ago, and in 2019, astronomers using data from the European Space Agency's Gaia spacecraft found direct observational evidence that it actually happens. They identified a population of white dwarfs that appeared to be cooling more slowly than expected, piling up at certain temperatures in a way that was consistent with crystallization releasing energy. Because here's the key thing about crystallization. When a substance transitions from a liquid state to a solid state, it releases latent heat. This is the same principle as water releasing heat when it freezes into ice. The phase transition from liquid to solid releases energy. In the case of a white dwarf, as the carbon and oxygen interior crystallizes, latent heat is released. This heat flows outward to the surface and is radiated away. But the process of releasing this latent heat effectively adds energy back into the white dwarf. It's like the white dwarf has a hidden battery that turns on at a certain temperature. The crystallization doesn't last forever. Once the entire interior has solidified, the latent heat source is exhausted. But while it's happening, it significantly slows the cooling. The white dwarf has to radiate away not only its residual thermal energy, but also the additional energy released by crystallization. Estimates suggest that crystallization can add billions of years to the cooling time of a white dwarf. Billions of years of additional delay on top of a process that was already going to take trillions of years. There's another factor related to crystallization that makes things even more interesting. As the white dwarf crystallizes, the composition of the crystal can differ from the composition of the remaining liquid. Specifically, oxygen tends to crystallize preferentially. The forming crystal lattice is enriched in oxygen, while the remaining liquid becomes enriched in carbon. Since oxygen nuclei are heavier than carbon nuclei, the oxygen-rich crystal is denser. It sinks toward the center of the white dwarf. Meanwhile, the lighter carbon-rich liquid rises. This creates a process called gravitational settling or chemical differentiation. And this process also releases gravitational potential energy. The heavier material falling inward and the lighter material rising outward converts gravitational energy into thermal energy. This is yet another source of heat that the white dwarf must radiate away before it can continue cooling. It's another delay, another slowdown, another reason the journey toward a black dwarf takes even longer than you'd expect from simple thermal radiation alone. And we're still not done with the factors that slow cooling. Because a white dwarf isn't just a bare exposed ball of degenerate matter. It has a thin atmosphere, a very thin layer of non-degenerate gas sitting on top of the incredibly dense interior. This atmosphere is typically made of hydrogen, helium, or a mixture of both. It's incredibly thin compared to the size of the white dwarf. If the white dwarf is the size of Earth, the atmosphere might be comparable in thickness to the coat of paint on a basketball. It's vanishingly thin, but it matters enormously for the cooling process. This thin atmosphere acts as an insulating blanket. Heat from the interior has to pass through this atmospheric layer before it can be radiated into space. And the atmosphere is not perfectly transparent to radiation. It absorbs and re-emits photons. It has opacity. This means that the rate at which energy escapes from the white dwarf is governed not just by the temperature of the interior, but by the properties of the atmosphere. How thick it is, what it's made of, how opaque it is to different wavelengths of radiation. And it turns out that this atmospheric blanket is remarkably effective at trapping heat. The composition of the atmosphere makes a significant difference. White dwarfs with hydrogen-rich atmospheres cool differently from white dwarfs with helium-rich atmospheres. Hydrogen is more opaque to certain wavelengths of radiation, which means a hydrogen-rich atmosphere traps heat more effectively. A white dwarf with a thicker hydrogen envelope will cool more slowly than one with a thinner envelope, or one with a helium atmosphere. The atmosphere doesn't just slow the cooling, it controls the cooling. It acts as the bottleneck. The degenerate interior might have plenty of thermal energy to radiate, but the energy can only escape as fast as the atmosphere allows. Think of it like a hot water bottle wrapped in a blanket. The water might be very hot, but the blanket controls how quickly that heat escapes into the room. A thicker blanket means slower cooling. A thinner blanket means faster cooling. The white dwarf's atmosphere is that blanket, and for many white dwarfs, it's a very effective one. This atmospheric insulation adds yet more time to the cooling process. It doesn't just add a few percent, it can significantly alter the timescale, stretching the cooling time by substantial factors depending on the specific composition and thickness of the atmospheric layer. So let's put all of this together. A white dwarf is cooling by radiating thermal energy from its surface, but the rate of radiation drops as the fourth power of temperature, creating a decelerating cooling curve. On top of that, crystallization of the interior releases latent heat that the white dwarf has to radiate away before it can continue cooling. Gravitational settling during crystallization releases additional energy that further delays the process. And the thin atmospheric envelope acts as an insulating blanket that controls how quickly heat can escape from the interior. Every single one of these factors pushes in the same direction. They all make the cooling slower. They all extend the time required to reach the black dwarf state. They all conspire to ensure that the journey from a hot, glowing white dwarf to a cold, dark black dwarf takes an almost incomprehensible length of time. Now, I need to put these timescales in context, because numbers like trillions and quadrillions of years don't mean anything to a human brain without something to compare them to. The universe is about 13.8 billion years old. That's 13.8 followed by 9 zeros. In scientific notation, that's about 1.38 times 10 to the 10th power years. The estimated cooling time for a white dwarf to reach something approaching the black dwarf state is somewhere in the range of 10 to the 15th to 10 to the 25th years, depending on the white dwarf's mass, composition, and atmospheric properties. Let's take a conservative estimate and say 10 to the 15th years. That's a quadrillion years, a 1 followed by 15 zeros. Compare that to the current age of the universe. 13.8 billion years is about 1.4 times 10 to the 10th power years. A quadrillion years is 10 to the 15th. The ratio is about 72,000. The universe would need to be roughly 72,000 times older than it currently is before the first black dwarfs could form. To put that differently, The universe has existed for approximately 0.0014% of the time required for a black dwarf to form, less than 0.002%. The universe isn't just young compared to the black dwarf timescale, it's embryonic, it's barely gotten started. Let me try another comparison. If the entire time required for a white dwarf to cool into a black dwarf were compressed into a single calendar year, then the current age of the universe, all 13.8 billion years of it, would represent about the first 7 minutes of January 1st. Everything that has ever happened, the Big Bang, the formation of the first stars, the birth and death of billions of stellar generations, the formation of galaxies, the origin of life on Earth, the entire history of human civilization, all of it fits into the first 7 minutes of a year-long process. The white dwarf hasn't even started its first day of cooling in any meaningful sense, relative to the total time required. We're watching the opening minutes of an event that will last all year. Or try this. If you scaled the cooling time of a white dwarf down to a human lifetime, say 80 years, then the current age of the universe would correspond to roughly the first 10 hours after birth. Less than half a day. The universe has been alive for less than half a day out of an 80-year lifetime. The white dwarf has been cooling for a few hours in a process that will take a full human lifespan. The baby hasn't even left the delivery room yet, and you're asking about retirement. These comparisons are not exaggerations, they're straightforward mathematics. The timescale mismatch between the current age of the universe and the cooling time of a white dwarf is genuinely this extreme. It's not a matter of waiting a few more billion years. It's not like we're almost there and just need to be patient. The universe has barely begun the process. The vast majority of the cooling journey lies in the future. The overwhelmingly vast majority. And the oldest, coldest white dwarfs we can observe, the ones that have been cooling for 10 or 11 billion years, are still glowing at temperatures of several thousand degrees. They've completed perhaps the first fraction of a percent of their cooling journey. This brings up something else worth understanding: the cosmic microwave background radiation. This is the faint afterglow of the Big Bang, a bath of microwave photons that fills all of space. It has a temperature of about 2.7 Kelvin, which is about minus 454 degrees Fahrenheit. Every object in the universe is immersed in this radiation. It's everywhere. And it sets a floor for how cold anything can get. A white dwarf can't cool below the temperature of the cosmic microwave background, because it's constantly absorbing photons from that background. It's like trying to cool a drink below room temperature by leaving it on the counter. The room itself keeps the drink from getting any colder. However, the cosmic microwave background is itself cooling as the universe expands. The expansion of space stretches the wavelengths of these photons, reducing their energy and lowering the temperature of the background radiation. Today, it's about 2.7 Kelvin. Billions of years from now, it will be lower. Trillions of years from now, it will be far lower. So the floor isn't fixed, it's dropping. But it's dropping slowly. And the white dwarf's own cooling is also slow. The two processes are both moving toward zero temperature, but neither will get there. Absolute zero is a theoretical limit that can be approached but never reached, according to the third law of thermodynamics. In practice, what happens is that the white dwarf and the cosmic background radiation both approach zero asymptotically, getting closer and closer, but never arriving. the white dwarf will eventually reach thermal equilibrium with the background radiation, meaning it will be absorbing and emitting energy at exactly the same rate. At that point, it's as cold as it can get. For practical purposes, that's the black dwarf state. It's not emitting any net radiation. It's in thermal equilibrium with the coldest thing in the universe, the background radiation itself. It's dark. It's cold. It's effectively invisible. But even reaching this equilibrium takes an extraordinarily long time. The white dwarf has to radiate away all of its stored thermal energy, all the latent heat from crystallization, all the gravitational energy from chemical differentiation, all of it through an insulating atmospheric blanket, while the rate of radiation drops as the fourth power of its steadily decreasing temperature. Every factor in the equation says the same thing. Slow, slower, even slower. There's one more thing worth mentioning about the cooling process. As a white dwarf approaches very low temperatures, quantum mechanical effects become increasingly important. At extremely low temperatures, the lattice vibrations of the crystallized interior change character. The specific heat of the crystal, which describes how much energy it takes to change the temperature by 1 degree, begins to drop. In a classical material, the specific heat is roughly constant, but in a quantum crystal at very low temperatures, the specific heat drops as the cube of the temperature. This is described by something called the Debye model. What this means is that at very low temperatures, it takes less and less energy to change the temperature by 1 degree. On one hand, this means there's less energy that needs to be radiated away. On the other hand, the rate of radiation has also dropped enormously. The net effect is complex, but the overall conclusion remains the same. The cooling continues to decelerate. The approach to zero temperature remains asymptotic. The process takes an almost unimaginable amount of time. Let me try one final comparison to drive this home. Consider the age of the Earth, about 4.5 billion years. In that time, life arose from simple chemistry, evolved from single-celled organisms to complex multicellular life, produced dinosaurs that ruled for over 160 million years, survived mass extinctions, and eventually gave rise to humans. All of human civilization, every empire, every discovery, every war, every work of art happened in the last few thousand years. The age of the Earth contains all of this. Now multiply the age of the Earth by roughly 1 million. That gives you about 4.5 quadrillion years. That's still only a fraction of the time required for the slowest cooling white dwarfs to become black dwarfs. The entire history of the Earth, from molten rock to complex civilization, repeated 1 million times over, and you're still not at the point where a black dwarf exists. The universe's current age of 13.8 billion years allows white dwarfs to cool from perhaps 180,000 degrees down to a few thousand degrees. That sounds like a lot. They've crossed most of the temperature range in absolute terms. 180,000 minus 4,000 is 176,000 degrees of cooling. That seems like most of the journey. But it's not, because the time required is not proportional to the temperature drop. It's the final cooling, the last few thousand degrees, the final crawl toward absolute zero, that takes by far the longest. The first 99% of the temperature drop might take 10 billion years. The last 1% might take a quadrillion. It's profoundly counterintuitive. You've watched the temperature plummet from 180,000 degrees to 4,000 degrees in 10 billion years, and you think surely the last 4,000 degrees can't take much longer. But it does. It takes incomprehensibly longer. Because the physics of thermal radiation is unforgiving. The colder you get, the harder it becomes to cool further. The universe has run its 13.8 billion years, and the oldest white dwarfs are sitting at a few thousand degrees, looking like they've almost finished. They haven't. They're at the top of a mountain that extends downward for 1,000,000 times farther than they've already climbed. The easy part is over. The hard part, the slow part, the part that takes trillions and quadrillions of years, that part hasn't even started in earnest. That is the slowest fade in the universe. A white dwarf losing its heat one photon at a time, each photon carrying less energy than the last. Each second of cooling taking longer than the one before, with crystallization and gravitational settling and atmospheric insulation all piling on to slow things down even further. It's a process that started billions of years ago when the first white dwarfs formed in the young Milky Way, and it will continue for timescales so vast that the current age of the universe doesn't even register as a meaningful fraction. The black dwarf is out there, waiting at the end of this journey. But the journey has barely begun, and the road ahead is longer than anything else in the physical universe, so now you understand the process. A white dwarf forms from the exposed core of a dead star. It starts out incredibly hot. It cools by radiating thermal energy from its surface. That cooling decelerates because the rate of radiation drops as the fourth power of temperature. Crystallization releases latent heat that adds billions of years to the process. Gravitational settling releases additional energy. A thin, insulating atmosphere controls how fast heat can escape. And the net result is a cooling timescale measured in quadrillions of years or more, far, far longer than the current age of the universe. This means that no white dwarf has finished cooling. Not one, anywhere, in any galaxy, in any corner of the observable universe. The black dwarf remains a purely theoretical object, an object with a name, a physical description, a well-understood formation mechanism, and zero examples in existence. And that paradox, the idea that science can define something so precisely and yet that thing cannot exist yet, is one of the strangest situations in all of astrophysics. Let's sit with that for a moment, because it's genuinely unusual. Most objects in astronomy are discovered first and explained later. Someone looks through a telescope, sees something unexpected, and then the theorists go to work figuring out what it is. Pulsars were discovered by accident in 1967 when Jocelyn Bell Burnell noticed a repeating radio signal coming from a fixed point in the sky. It took time to figure out these were rapidly rotating neutron stars. Black holes were predicted by general relativity decades before any observational evidence confirmed their existence. But even then, the first strong candidates were identified through their effects on nearby matter within the 20th century. Exoplanets were hypothesized for centuries, but only confirmed in the 1990s. In every case, the gap between prediction and observation was eventually closed. We predicted something, and then we found it. Or we found something, and then we explained it. But black dwarfs are different. The gap between prediction and observation cannot be closed. Not now. Not in 1 billion years. Not in 100 billion years. The physics is settled. The prediction is solid. Everyone agrees that black dwarfs will eventually form. But the confirmation, the actual observation of a real black dwarf, is separated from us by a span of time so enormous that it dwarfs the entire history of the cosmos up to this point. We will never observe a black dwarf. No human being, no civilization that exists anywhere near our era of cosmic history will ever see one. They are objects that belong entirely to the deep future. We know they're coming. We just can't be around when they arrive. This raises the question of what exactly a black dwarf would be if one did exist. What would it look like? How would it behave? What would you experience if you could somehow visit one? And the answer is both simple and haunting. A black dwarf would be almost nothing, almost undetectable, almost invisible. It would be a sphere roughly the size of Earth, maybe a bit smaller, maybe a bit larger depending on its mass. Its surface would be solid, or very nearly so, a crystalline lattice of carbon and oxygen atoms locked into a rigid structure. The density would still be extraordinary, about 1 million times the density of water, the same as the white dwarf it used to be. The mass would still be significant, roughly half the mass of the Sun packed into an Earth-sized volume. Gravity on the surface would be about 170,000 times stronger than gravity on Earth's surface. If you could somehow stand on a black dwarf, and you can't because the gravity would crush you instantly, you would weigh roughly 25 million pounds. Every bone in your body would be shattered. Every organ would be flattened. You would be compressed into a thin layer on the surface in a fraction of a second. But you wouldn't see anything, because the black dwarf wouldn't be emitting any light. Its temperature would be essentially the same as the cosmic microwave background, just a few degrees above absolute zero, perhaps even less as the background radiation itself cools over the eons. At such a low temperature, the thermal radiation emitted by the black dwarf would be in the microwave and radio wavelengths, at intensities so low they would be virtually indistinguishable from the background noise of the universe itself. No visible light, no infrared glow, no warmth, nothing your eyes could detect. If you were floating in space near a black dwarf, you wouldn't see it. It would be a dark sphere blotting out the stars behind it. That's the only way you'd know it was there. Stars that should be visible in that direction would be missing, blocked by this cold, dark, invisible mass. Or you might detect it through its gravitational influence. If the black dwarf was part of a binary system, its companion might orbit it, revealing the black dwarf's presence through gravitational effects. If it passed near another object, it might bend light through gravitational lensing, acting as a massive invisible lens that distorts the images of more distant stars and galaxies. But the black dwarf itself would produce nothing. No light, no heat, no signal. It would be as close to nothing as a star mass object can get while still existing. This is a profound kind of death for a star. Not the violent death of a supernova, where a massive star explodes in a burst of energy that briefly outshines an entire galaxy. Not the dramatic death of a star collapsing into a black hole, where space-time itself is warped beyond recognition. This is a quiet death, a slow death, a death that takes longer than any other process in the universe. The star lives, it dies, it becomes a white dwarf, and then it spends an eternity slowly going dark. No explosion, no drama, just an imperceptibly gradual fading from dim to dimmer to invisible, the longest farewell in the cosmos. Now, I need to clear up something important, because the term black dwarf sounds similar to other astronomical terms, and people frequently confuse them. A black dwarf is not a black hole. These are completely different objects with completely different physics and completely different origins. A black hole forms when a very massive star, typically at least 20 to 25 times the mass of the Sun, exhausts its nuclear fuel and its core collapses. In these massive stars, the core is so heavy that neither electron degeneracy pressure nor even neutron degeneracy pressure can halt the collapse. Gravity wins completely. The core collapses to a point of theoretically infinite density called a singularity, surrounded by a boundary called the event horizon beyond which nothing can escape, not even light. Black holes are defined by their extreme gravity. They warp space-time dramatically. They can consume matter and energy from their surroundings. They have been observed through their effects on nearby stars, through the radiation emitted by superheated gas spiraling into them, and even directly imaged, as the Event Horizon Telescope collaboration demonstrated in 2019 with the black hole at the center of the galaxy M87. A black dwarf, by contrast, is a cooling remnant. It doesn't consume anything. It doesn't warp space-time in any extreme way. It's just a cold, dense object sitting in space, dark and inert. The only thing a black dwarf and a black hole have in common is the word black, meaning they don't emit visible light. Beyond that, they're fundamentally different objects. A black hole is a gravitational extreme, a point where the laws of physics as we understand them break down. A black dwarf is a thermodynamic endpoint, the final resting state of a white dwarf that has simply run out of heat. One is defined by gravity so strong that space-time collapses. The other is defined by a temperature so low that radiation ceases. They're about as different as two astronomical objects can be. Similarly, a black dwarf is not a brown dwarf. This is another common confusion because the names sound alike. A brown dwarf is sometimes called a failed star. It's an object that formed the same way a star forms, from the gravitational collapse of a cloud of gas and dust. But it didn't accumulate enough mass to ignite sustained hydrogen fusion in its core. The minimum mass required for hydrogen fusion is roughly 80 times the mass of Jupiter, or about 8% of the Sun's mass. Brown dwarfs fall below this threshold. They might have masses anywhere from about 13 times the mass of Jupiter up to about 80 times the mass of Jupiter. They're too massive to be planets, but not massive enough to be stars. Brown dwarfs do generate some heat through gravitational contraction and through the fusion of deuterium, a heavy isotope of hydrogen, in their early lives, but they never achieve the sustained hydrogen fusion that defines a true star. They glow faintly, mostly in the infrared, and they cool over time. But their origin is completely different from a black dwarf's origin. A brown dwarf was never a star. It never went through a main sequence phase. It never fused hydrogen in its core for billions of years. It never became a red giant. It never shed its outer layers. It never exposed a degenerate core. A brown dwarf is a distinct class of object that formed independently and has always been what it is. A black dwarf, on the other hand, is the far future end state of a white dwarf, which itself was once a fully functional star that lived and died over billions of years. The two objects share almost nothing in common except the word dwarf, which in astronomy simply refers to something relatively small. The naming is unfortunate because it creates confusion where none should exist. Black dwarfs, black holes, and brown dwarfs are three entirely different things with three entirely different formation mechanisms, three entirely different physical properties, and three entirely different roles in the story of the cosmos. Now, let's talk about how astronomers study the cooling of white dwarfs and how they arrive at these enormous timescale estimates. Because you might reasonably ask how we can be so confident about a process that takes quadrillions of years when we've only been doing serious astronomy for a few centuries. The answer lies in the physics of thermal radiation and the observational study of white dwarf populations. Astronomers don't need to watch a single white dwarf cool in real time. That would be impossible. The cooling is far too slow to detect changes within a human lifetime or even within the lifetime of human civilization. Instead, they study populations of white dwarfs at various stages of cooling and use physics to connect the dots. Think of it like studying human aging without watching a single person grow old. If you took a photograph of a crowded city street, you'd see people of all ages, babies, children, teenagers, adults, elderly people. None of them are aging visibly in the photograph. But by studying the distribution of ages, by understanding the biology of aging, you can figure out the entire human lifespan without watching any individual person from birth to death. Astronomers do the same thing with white dwarfs. They observe thousands of white dwarfs at various temperatures and luminosities. Hot, bright, recently formed white dwarfs, warm, moderately dim, middle-aged white dwarfs, cool, faint, old white dwarfs. By measuring the temperatures and brightnesses of these objects, and by knowing the physics of how degenerate matter radiates heat, they can construct detailed cooling models that predict how a white dwarf's temperature and luminosity change over time. These models are quite sophisticated. They incorporate the Stefan Boltzmann law governing thermal radiation. They include the effects of crystallization and the release of latent heat. They account for gravitational settling and chemical differentiation. They model the atmospheric opacity, which controls how quickly heat escapes through the insulating envelope. They include quantum mechanical effects on the specific heat of the crystalline interior at low temperatures. And they match these models against observations. The models predict that white dwarfs should pile up at certain temperatures, spending more time at lower temperatures because the cooling decelerates. Observations confirm this. The models predict that crystallization should cause a temporary slowdown in cooling at certain temperature ranges. The Gaia spacecraft's data confirmed this in 2019. The models predict a relationship between a white dwarf's mass, composition, atmospheric type, and cooling rate. Observations of binary systems where the age of the white dwarf can be independently estimated confirm these relationships. So the models work. They match what we observe in the temperature range we can actually test. And since the physics underlying those models, thermodynamics, quantum mechanics, nuclear physics, is well established and thoroughly tested in laboratories on Earth, astronomers are confident that the models remain valid at temperatures far below what we've observed. Extrapolating these models to their logical endpoint, to temperatures approaching absolute zero, is what gives us the quadrillion-year timescale for black dwarf formation. It's not a guess, it's not speculation, it's an extrapolation based on physics that has been tested and confirmed at every stage where testing is possible. But there is one thing the models can't tell us with perfect precision. The exact cooling time depends on details that vary from one white dwarf to another. The mass of the white dwarf matters. More massive white dwarfs have higher internal temperatures and more stored thermal energy, but they also have smaller radii and therefore smaller surface areas to radiate from. The composition matters. A white dwarf with a carbon-oxygen core cools differently from one with an oxygen-neon core. The atmospheric composition matters enormously. A thick hydrogen envelope traps heat more effectively than a thin helium envelope. Some white dwarfs have almost no atmosphere at all, and cool faster. So the cooling time to reach a black dwarf state isn't a single number. It's a range. Some white dwarfs will cool faster than others. The fastest cooling white dwarfs, those with low mass, thin atmospheres, and favorable compositions, might reach the black dwarf state in perhaps 10 to the 15th years, a quadrillion years. The slowest cooling ones might take 10 to the 20th years or even longer. But regardless of where in this range any particular white dwarf falls, the number is vastly larger than the current age of the universe. Even the most optimistic estimate still requires the universe to be roughly 70,000 times older than it currently is. Let's talk about the coldest white dwarfs we've actually observed, because these objects are the closest things to black dwarfs that exist in the universe today, and they help us understand how far the cooling process has gotten. The coldest known white dwarfs have surface temperatures in the range of about 3,000 to 4,000 Kelvin. That's about 4,900 to 6,700 degrees Fahrenheit. For comparison, the surface of the Sun is about 5,800 Kelvin. So the coldest white dwarfs are still roughly half to 2/3 the surface temperature of the Sun. They're not hot by stellar standards, but they're still thousands of degrees above anything you'd encounter in everyday life. They're certainly not cold, not by any definition of the word that matters for the black dwarf question. These ancient white dwarfs are extremely faint. They emit most of their radiation in the infrared and are challenging to detect even with modern telescopes. Finding them requires dedicated surveys using sensitive instruments. The Hubble Space Telescope has identified some of the oldest, coolest white dwarfs in globular clusters, dense collections of ancient stars. These white dwarfs are estimated to be about 10 to 12 billion years old, based on the ages of the clusters they inhabit. And they're still glowing. Faintly, but glowing. In 2014, astronomers announced the discovery of a white dwarf companion to a pulsar, designated PSRJ 2222-0137. This white dwarf was estimated to have a surface temperature of approximately 2,690 Kelvin, making it one of the coolest white dwarfs ever found at the time. Its age was estimated at roughly 11 billion years. 11 billion years of cooling, and it still had a surface temperature of over 4,000 degrees Fahrenheit. This single observation tells you almost everything you need to know about why black dwarfs don't exist yet. 11 billion years is a staggering amount of time. It's more than 80% of the age of the universe. This white dwarf has been cooling for longer than the Earth has existed, longer than the Sun has existed, longer than most stars in the galaxy have been alive. And it's still over 4,000 degrees Fahrenheit. It's still detectable. It's still radiating. It has trillions of years of cooling ahead of it, before it could become a black dwarf. Surveys from spacecraft like Gaia, which is mapping the positions, distances, and properties of over 1 billion stars in the Milky Way, have identified thousands of white dwarfs across a wide range of temperatures. The distribution of these white dwarfs, how many are found at each temperature, confirms the theoretical models. There are many hot young white dwarfs, fewer warm middle-aged ones, and fewer still that are cool and ancient. The distribution tapers off at the cool end, Not because white dwarfs stop cooling, but because the universe hasn't existed long enough for any to have cooled below a certain temperature. There's a cutoff, a minimum temperature below which no white dwarfs are found, and that cutoff matches what the cooling models predict for the oldest possible white dwarfs given the age of the universe. This cutoff is itself a tool for measuring the age of the galaxy, because the temperature of the coolest white dwarfs tells you how long they've been cooling, and that tells you the minimum age of the stellar population they belong to. It's called white dwarf cosmochronology, using dead stars as clocks, and those clocks consistently tell us the same thing. The oldest white dwarfs in the Milky Way are about 10 to 11 billion years old. They've cooled a lot, but they haven't cooled enough. Not even close. So what would it actually take to detect a black dwarf if one existed? This is a thought experiment since none exist, but it's worth exploring because it highlights just how invisible these objects would be. A black dwarf would emit no significant electromagnetic radiation, no visible light, no infrared, no ultraviolet, no X-rays, no radio waves worth detecting. Its thermal radiation would be at a temperature essentially equal to the cosmic microwave background, which means it would blend perfectly into the faint microwave glow that fills all of space. Trying to detect a black dwarf by its thermal emission would be like trying to hear someone whispering in a stadium full of people whispering at exactly the same volume. The signal would be indistinguishable from the background noise. You might detect a black dwarf through its gravity. It still has mass, roughly half the mass of the Sun compressed into an Earth-sized sphere. That mass produces a gravitational field. If a black dwarf were part of a binary system, its companion star or other object would orbit it, and we could infer the black dwarf's presence from the companion's orbital motion. This is similar to how astronomers first detected black holes by observing the behavior of visible stars that appeared to be orbiting an unseen companion. But a black dwarf's gravity, while strong near its surface, isn't exotic. It doesn't produce the extreme gravitational effects that make black holes detectable from great distances. A black dwarf sitting alone in interstellar space would be extraordinarily difficult to find. It wouldn't pull in surrounding gas and heat it up the way a black hole does. It would just sit there, cold, dark, inert, a massive invisible obstacle drifting through the galaxy. Gravitational lensing offers another theoretical detection method. When a massive object passes between us and a more distant light source, the gravity of the intervening object bends the light, acting as a lens. This can magnify or distort the image of the background source. If a black dwarf passed between Earth and a distant star, we might notice the star briefly brightening or its image distorting as the black dwarf's gravity bent the starlight around it. This technique, called gravitational microlensing, is already used to detect objects that don't emit light, including the rogue planets and other dim objects. In principle, it could detect a black dwarf. But in practice, microlensing events are rare and brief. They require precise alignment between the observer, the lensing object, and the background source. Detecting a single black dwarf through microlensing would require monitoring millions of stars continuously and getting lucky enough to catch the alignment. It would be extraordinarily difficult even if black dwarfs existed in large numbers. The bottom line is this: a black dwarf would be one of the hardest objects in the universe to detect. It produces nothing. It emits nothing. It signals its presence only through gravity, and even that signal is subtle compared to the dramatic effects produced by more exotic objects like black holes and neutron stars. A black dwarf is, in a sense, the universe's most perfect hiding place. A star mass object that has become completely invisible. A remnant so cold and so dark that it's essentially indistinguishable from empty space unless you happen to pass very close to it, or unless it happens to lens a background star at exactly the right moment. In the far future, when the universe is filled with black dwarfs, the cosmos will be populated by trillions of massive invisible spheres drifting silently through the darkness, each one the final remnant of a star that once shone brightly, each one carrying the mass of a star, but producing none of the light, each one a gravestone for something that died so slowly that the dying took longer than the living. The universe of the deep future will be a dark place, not because matter has disappeared, but because the energy that made matter visible has been radiated away, diluted, and lost to the ever-expanding emptiness of space. The black dwarves will be there. They'll be everywhere, but you'd never know it by looking. That is the central paradox of the black dwarf. It's an object that physics guarantees will exist. The math is clear. The cooling models are robust. Every white dwarf in the universe is on a one-way journey toward the black dwarf state. The destination is certain, but the journey is so long that the destination exists only as a mathematical certainty, not as a physical reality. Not yet. Not for an almost inconceivable span of time. The universe has named something it cannot yet produce. It has described something it cannot yet show you. And it has set in motion a process, the cooling of white dwarfs, that it cannot complete for trillions upon trillions of years. The black dwarf is the universe's longest promise, a guarantee written in the laws of thermodynamics and quantum mechanics, sealed by the fundamental nature of degenerate matter, and delivered on a timescale that makes everything else in cosmic history look instantaneous. Every white dwarf is a promise in progress. Every photon that escapes from its cooling surface is one tiny step closer to fulfillment. But the steps are getting smaller, and the road is getting longer, and the destination is still so far away that the universe itself has barely started walking. Everything we've discussed so far has been about the present and the recent past. White dwarfs that exist today, cooling processes that are underway right now, observations made with telescopes we've already built. But the black dwarf belongs to the future, not the near future, not the kind of future where humans build better rockets or colonize Mars or develop fusion energy. The black dwarf belongs to a future so distant that the word future almost loses its meaning. A future measured not in thousands or millions or even billions of years, but in timescales so vast that entirely new units of measurement become necessary. To understand the black dwarf's place in the cosmos, we need to look forward, far forward, into the deep future of the universe itself. And what we find there is a story of slow, inevitable, irreversible change. A story in which the black dwarf is not an anomaly or a curiosity, but the dominant object in the cosmos. The final inheritor of a universe that has spent everything it had. Let's start with where we are right now in cosmic history. The universe is about 13.8 billion years old. Stars are being born, galaxies are shining. The cosmos is filled with light and activity and energy. This is the stelliferous era, the age of stars. It's the era we live in. And it feels permanent. When you look up at the night sky, the stars seem eternal. They were there before you were born. They'll be there after you die. They were there before human civilization began, and they'll be there long after it ends. but they're not eternal. The stelliferous era has a beginning and it will have an end. Stars form from clouds of gas, primarily hydrogen. When a region of gas is dense enough, gravity pulls it together and eventually ignites nuclear fusion. A star is born, but the supply of gas is finite. Every star that forms uses up some of the available hydrogen, and when stars die, some of that hydrogen is returned to space through stellar winds and supernova explosions, but not all of it. Some is locked away permanently in white dwarfs, neutron stars, and black holes. These stellar remnants don't recycle their material. They hold on to it forever. So with every generation of stars, the total supply of available gas decreases. New stars are still forming in the Milky Way at a rate of roughly 1 to 2 per year, but that rate has been declining. The peak of star formation in the universe occurred about 10 billion years ago, when galaxies were younger and gas was more abundant. Since then, the rate has dropped steadily. The universe has already passed its prime in terms of star formation. We're living in the slow decline. Over the next several trillion years, star formation will continue, but at a decreasing rate. Galaxies will gradually exhaust their gas supplies. The large spiral galaxies, like the Milky Way and Andromeda, will merge into giant elliptical galaxies. Those ellipticals will consume whatever remaining gas they have, forming a final generation of stars, and then star formation will effectively stop. The last stars to form will probably be red dwarfs. These are the smallest, dimmest, most fuel-efficient stars in the universe. A red dwarf with about 8% of the sun's mass can burn hydrogen for roughly 10 trillion years. That's nearly 1,000 times longer than the current age of the universe. Red dwarfs are the long-distance runners of the stellar world. They sip their fuel rather than gulping it. And because they're so common, making up about 70% of all stars in the Milky Way, they'll dominate the final stages of the stelliferous era. For trillions of years, the universe will be lit primarily by the dim red glow of these small, patient stars. But even red dwarfs die eventually. After about 10 trillion years, give or take, the last red dwarfs will exhaust their hydrogen and shut down. They'll leave behind white dwarfs, just like more massive stars do, though the process is slightly different for the lowest mass stars. When the last red dwarf dies, the stelliferous era ends. No more stars will form because there's no more gas. No more light will be generated by nuclear fusion. The universe will enter a new era. An era defined not by the living, but by the dead. This next era is sometimes called the degenerate era. It's the age of stellar remnants. The universe will still contain enormous amounts of matter, but that matter will be locked in objects that produce no new energy. White dwarfs, neutron stars, black holes, and eventually black dwarfs. The degenerate era begins roughly 10 trillion years from now, when the last stars die, and it lasts for an almost incomprehensible span of time. During this era, the dominant sources of whatever faint energy remains will be the slowly cooling white dwarfs. They'll still be warm at the start of the degenerate era, still radiating faintly, still emitting photons into the growing darkness. But they'll be cooling, getting dimmer, getting colder, decade by decade, century by century, millennium by millennium, across timescales that make the stelliferous era look like a brief flash. The degenerate era is estimated to last until somewhere around 10 to the 37th to 10 to the 40th power years. These numbers are so large that writing them out in words becomes almost absurd. 10 to the 37th years is 10 trillion years. 10 to the 40th is 10,000 times longer than that. During this unimaginable span, white dwarfs will slowly, methodically, relentlessly cool. And one by one, over quadrillions and quintillions of years, they will cross the threshold into the black dwarf state. The first black dwarfs to form will be those that had the most favourable conditions for rapid cooling. Low mass, thin atmospheres, compositions that radiate efficiently. These fastest cooling white dwarfs might reach the black dwarf state after perhaps a quadrillion years, 10 to the 15th power. But most white dwarfs will take far longer. The average white dwarf with a moderate mass and a typical hydrogen atmosphere might take 10 to the 18th or 10 to the 20th years. The slowest cooling ones, those with thick insulating envelopes and high masses, might take even longer. The formation of black dwarfs won't be a sudden event. It'll be a gradual transition, a slow dimming of the last lights, one by one, across trillions and quadrillions of years. The white dwarfs will go dark, each one crossing the threshold from barely glowing to not glowing at all, each one joining the growing population of invisible, cold, dense spheres drifting through a universe that has gone almost completely dark. By the time the degenerate era ends, the universe will be populated primarily by black dwarfs. Trillions of them in every galaxy, or rather in the gravitationally bound structures that used to be galaxies. Because by this point, galaxies as we know them will have changed beyond recognition. Stars within galaxies interact gravitationally over long timescales. Through random gravitational encounters over trillions of years, some objects will be ejected from their galaxies entirely, flung into intergalactic space at high velocities. Others will sink toward the center, gradually spiraling inward. Over timescales of about 10 to the 19th to 10 to the 20th years, most of the stellar remnants in a galaxy will either be ejected or will fall toward the central supermassive black hole. The galaxy will slowly dissolve. Its structure will erode. What was once a magnificent spiral containing hundreds of billions of stars will become a diffuse cloud of scattered black dwarfs drifting through expanding space, with a growing black hole at the center that has consumed a significant fraction of the galaxy's original mass. And then there are the black holes themselves. During the degenerate era, supermassive black holes at the centers of galaxies will continue to exist. They don't cool, they don't fade, they just sit there, their gravity undiminished, slowly consuming whatever falls into them. But even black holes are not eternal. In 1974, the physicist Stephen Hawking proposed that black holes emit radiation through a quantum mechanical process now known as Hawking radiation. This radiation is extraordinarily faint for large black holes. A supermassive black hole, like the one at the center of the Milky Way, with a mass of about 4 million times the mass of the Sun, emits Hawking radiation at a temperature far below the current cosmic microwave background. The radiation is so feeble that the black hole actually absorbs more energy from the cosmic background than it emits. It's gaining mass, not losing it. But in the far future, the cosmic microwave background will have cooled to essentially nothing as the universe continues to expand. The temperature of the background radiation will drop below the Hawking temperature of the black hole. At that point, the black hole will begin to lose mass faster than it gains it. It will slowly evaporate. This process is almost unimaginably slow. A stellar mass black hole would take roughly 10 to the 67th power years to evaporate. A supermassive black hole with a mass of 4 million solar masses would take about 10 to the 87th power years. The largest supermassive black holes, those with billions of solar masses, might take 10 to the 100th power years. That number, 10 to the 100th, has a special name. It's called a googol, and the timescale for the largest black holes to evaporate is roughly a googol years. These are the last objects in the universe to disappear. After the black holes are gone, the universe enters what's sometimes called the dark era, an era of nothing, just photons, neutrinos, and perhaps some subatomic particles, all spreading out through an ever-expanding, ever-cooling void. No structure, no light, no energy concentrations of any kind, just emptiness, stretching out toward eternity. But before we get to that ultimate emptiness, there's one more chapter in the Black Dwarf story, and it might be the most extraordinary chapter of all. In 2020, a theoretical physicist named Matt Kaplan published a paper exploring what might happen to black dwarfs in the truly extreme far future. His work suggested that black dwarfs might not simply sit there inert forever. They might, given enough time, undergo one final transformation. The physics goes like this. A black dwarf is made primarily of carbon and oxygen, locked in a crystalline lattice. Under normal circumstances, these elements cannot fuse. Carbon fusion requires temperatures of about 1 billion degrees Fahrenheit, and the black dwarf's temperature is essentially zero. Fusion seems impossible, but quantum mechanics allows something that classical physics does not. It allows particles to tunnel through energy barriers that they don't have enough energy to overcome classically. This is called quantum tunneling. It's a real, well-established phenomenon. It's how radioactive decay works. An alpha particle inside a nucleus doesn't have enough energy to escape classically, but quantum mechanics gives it a small probability of tunneling through the energy barrier anyway. Given enough time, it will tunnel. The same principle applies to the nuclei inside a black dwarf. Carbon and oxygen nuclei don't have enough thermal energy to overcome their electrostatic repulsion and fuse. But quantum tunneling gives them a tiny, vanishingly small probability of fusing anyway. On human timescales, this probability is so low that it's essentially zero. On timescales of billions or trillions of years, it's still essentially zero. But on timescales of 10 to the 1100th power years or more, and yes, that's 10 raised to the power of 1100, a number so large it makes a googol look like pocket change, quantum tunneling becomes significant. Over these absurdly vast timescales, the nuclei inside a black dwarf will occasionally fuse, one by one, atom by atom. The carbon and oxygen will slowly, excruciatingly slowly, undergo nuclear fusion through quantum tunneling. The fusion products will gradually build up heavier elements. Over unimaginable spans of time, the composition of the black dwarf will change. Carbon and oxygen will slowly become silicon and sulfur and calcium, then eventually iron. And iron is where things get critical. Iron is the end of the line for nuclear fusion. Fusing elements lighter than iron releases energy. Fusing iron or elements heavier than iron requires energy rather than releasing it. When enough of the black dwarf's interior has been converted to iron through this painfully slow quantum tunneling process, the object becomes unstable. It can no longer support itself. The iron core reaches a critical mass and collapses. And when it collapses, it triggers something astonishing. A supernova. A black dwarf supernova. The last explosion the universe will ever see. These black dwarf supernova, if Kaplan's calculations are correct, would be the final events in the physical universe. The last time matter converts to energy in a dramatic, violent release. The last flash of light in a cosmos that has been dark for timescales beyond any meaningful comparison. Each black dwarf supernova would be a brief, brilliant eruption, and then darkness again. Forever. Kaplan estimated that the first black dwarf supernovas would begin occurring around 10 to the 1100th power years from now. The last ones might occur around 10 to the 32,000th power years from now, because black dwarfs of different masses would undergo this process at different rates. The most massive black dwarfs would go first because their higher internal pressures would accelerate the quantum tunneling process. The least massive ones would go last, taking the longest to accumulate enough iron to trigger collapse. Let me try to put these numbers in perspective, even though doing so is almost futile. 10 to the 1100th power years. To write this number out in full, you would need to write a 1 followed by 1100 zeros. For comparison, the number of atoms in the observable universe is estimated at about 10 to the 80th power. The number 10 to the 1100th is incomprehensibly larger. If every atom in the observable universe were itself an entire universe, and you counted all the atoms in all those universes, and then repeated that process again and again, you still wouldn't come close to 10 to the 1100th. This is a number so far beyond human comprehension that it exists only as a mathematical abstraction. And yet, this is the timescale on which the black dwarf's final act plays out. The universe will be dark and empty and cold for a span of time that dwarfs everything that came before by a factor that cannot be meaningfully expressed. And then, one by one, in scattered locations throughout the void, the black dwarfs will detonate. Brief sparks of light in an infinite darkness. The last supernovae, the universe's final act of creation and destruction, and then silence. Permanent, irreversible silence. There's something deeply poignant about this picture. The black dwarf supernova is the universe's last word. Not a whimper, not a slow fade, but a brief, defiant flash. After spending longer in darkness than any human mind can conceive, the remnant of a long-dead star finds one last way to release energy. One last burst of light. One last reminder that the universe once blazed with stars and galaxies and life. And then it's over. The matter that was once a star, that was once part of a nebula, that was once scattered across space by a previous supernova billions of years earlier, that matter collapses one final time, and whatever is left, neutron star or small black hole, drifts on through the expanding void. No more transformations, no more events, nothing. Step back from these incomprehensible timescales for a moment, and think about what the black dwarf represents in the grand narrative of the cosmos. Every star that has ever existed, or will ever exist, goes through a life cycle. It's born from a cloud of gas. It burns bright for millions or billions of years. It dies, leaving behind a remnant. For the most massive stars, that remnant is a black hole. For moderately massive stars, it's a neutron star. But for the vast majority of stars in the universe, all the ones with masses between about 8% and 800% of the sun's mass, the remnant is a white dwarf. White dwarfs are the most common stellar remnants in the universe. The Milky Way alone contains an estimated 10 billion white dwarfs. The observable universe probably contains something on the order of 10 billion trillion. And every single one of them is on its way to becoming a black dwarf. This means that in the far future, black dwarfs will be the most common stellar remnant in the cosmos. They will vastly outnumber neutron stars and black holes combined. The universe's population of dead stars will be dominated by these cold, dark, crystalline spheres. They will be everywhere, in every form of galaxy, in every corner of the cosmos, trillions upon trillions of them, drifting in the dark, invisible and silent, each one carrying the mass of a star, but producing none of the energy. And here is where the story of the black dwarf connects back to us, back to the present, back to the universe we actually live in. Because right now, the universe is young. The stelliferous era is still ongoing. Stars are still being born. Galaxies are still shining. The cosmos is still filled with light and energy and structure. We are living in the brief window of cosmic history when the universe is active and luminous. A window that opened about 200 million years after the Big Bang, when the first stars ignited, and that will close roughly 10 trillion years from now, when the last red dwarfs die. That's a window of maybe 10 trillion years. It sounds enormous. It is enormous by human standards. But compared to the degenerate era that follows, compared to the quadrillions and quintillions of years during which white dwarfs cool into black dwarfs, compared to the utterly incomprehensible timescales on which black dwarf supernovae occur, the stelliferous era is a flash, a spark, a brief flicker of light between two immensities of darkness. The universe spent its first few 100 million years in darkness before the first stars formed. It will spend its remaining existence, an existence measured in numbers that cannot be meaningfully written, in darkness after the last stars die. The time of light, the time of stars, the time of us, is a vanishingly thin sliver sandwiched between two eternities of cold and dark. Try to imagine what the degenerate era actually feels like. Not the mathematics of it, not the physics, but the texture, the lived reality of a universe in that state. There are no stars, anywhere, in any direction. The night sky, if you could somehow be there to see it, would be perfectly black. Not the kind of dark you experience on a moonless night in the countryside, where you can still see the Milky Way and thousands of stars scattered across the sky. This would be a darkness so complete that there would be nothing to see at all. No points of light, no faint glow on the horizon, no nebulae, no galaxies, just blackness. Pure, total, unbroken blackness in every direction for distances that would take light trillions of years to cross. And this darkness wouldn't last for a night. It wouldn't last for a year or a century. It would last for timescales so vast that if you wrote down the number of years, the number itself would be longer than any book ever written. The universe in the degenerate era is a place of absolute stillness. Nothing is happening. Nothing is changing in any way you could perceive. White dwarfs are cooling, but so slowly that you could watch one for 1 million years and measure no difference. Black dwarfs are sitting in the void, but they produce no signal, no sign, no evidence of their existence beyond gravity. The cosmos is full of matter, full of mass, full of objects that once blazed with nuclear fire. But all of that fire is out, all of that light is gone. And the silence that replaces it is not the temporary silence between events. It is the permanent silence of a universe that has exhausted its capacity for change on any timescale that matters. This gives the black dwarf a peculiar kind of cosmic significance. It is the inevitable endpoint, the destination that every sun-like star is heading toward. Our own sun, 5 billion years from now, will become a red giant. It will shed its outer layers, It would leave behind a white dwarf roughly the size of Earth, and that white dwarf will begin to cool. It will glow for billions of years, then trillions, then quadrillions, and eventually, so far in the future that the number of years required has more digits than there are atoms in your body, it will go dark. It will become a black dwarf, the sun's black dwarf, the final remnant of the star that made life on Earth possible, the same star that warms your skin on a summer afternoon, that drives the weather patterns and the ocean currents, that powers photosynthesis and therefore all of biology. That star will one day be a cold, dark, invisible sphere drifting through empty space, still carrying its mass, still carrying the gravitational memory of what it once was, but producing nothing, emitting nothing, signaling nothing. Every white dwarf you could observe tonight through a telescope is on this same journey. Every single one. The bright, hot ones that formed recently from the deaths of sun-like stars. The ancient dim ones that have been cooling for 10 billion years in the halos of old, globular clusters. The ones in binary systems, the ones orbiting other stars, the ones drifting alone through interstellar space. All of them. Cooling. Fading. Approaching a destination they will not reach for timescales that defy human language. The black dwarf is not just an object. It's a statement about the nature of time. It tells us that the universe operates on timescales so vast that everything we know, everything we are, everything we've ever experienced or built or imagined fits into the tiniest fraction of the cosmic timeline. The universe is patient beyond any human concept of patience. It will build its black dwarfs one photon at a time, 1 degree of cooling at a time, across spans of time that make the entire age of the cosmos look like nothing, and yet none exist. That's the part that stays with you. The universe contains trillions of white dwarfs, all of them cooling, all of them on the path toward the black dwarf state, and not one of them has arrived. Not one. The universe is 13.8 billion years old, and it hasn't been able to finish cooling a single white dwarf. The destination is certain, the physics guarantees it, but the arrival date is so far in the future that it belongs to a chapter of cosmic history that hasn't even been imagined yet by the universe itself. There is something in this that humbles you in a way that nothing else in astronomy quite manages. Black holes are dramatic, supernovae are spectacular, the Big Bang is overwhelming, but the black dwarf is something else entirely. It's quiet, it's patient, it's the universe's longest process playing out in the universe's most boring way. No explosions, no collisions, no drama. Just a slow, steady loss of heat. Photon by photon, degree by degree. Across timescales that reduce everything else to insignificance. And the result is an object that cannot yet exist. An object that the universe is building with infinite patience and has not yet completed. An object that will one day outnumber every other type of stellar remnant in the cosmos, but that today has a population of exactly 0. And yet knowing this changes something about how you see the present. Because the present is where the light is. The present is where the stars still burn. The present is the brief, extraordinary, unrepeatable moment when the universe is awake and active and full of energy. Every star you see tonight is a temporary thing. Every photon that reaches your eye from a distant sun is a gift from a process that will one day stop. The light is not permanent. It never was. It's a phase, a season, a fleeting period in the life of a cosmos that will spend almost all of its existence in darkness. And we happen to be here during the light. We happen to exist during the one brief window when stars shine and planets orbit, and life is possible. Not before the first stars, not after the last ones die. Right now. In the middle of the only era when any of this could happen. That is not nothing. That is extraordinary. The Black Dwarf tells us what comes after. And what comes after is silence. But we are not in the after. We are in the during. The brief, luminous during. And every moment of it matters more because of what the Black Dwarf tells us about how long the darkness will last. The Black Dwarf is the universe's ultimate exercise in patience. It is the promise that the cosmos has made to the future. A promise written in the laws of thermodynamics, sealed by the quantum mechanics of degenerate matter, and payable only after the passage of time so vast that no clock could measure it. Every white dwarf is a down payment on that promise. Every photon that escapes from a cooling surface is one step closer to fulfillment. But the debt is enormous and the payments are small and getting smaller. The balance won't reach zero for trillions upon trillions of years. And until it does, the Black Dwarf will remain what it is tonight. A name for something that doesn't exist. A description of something that has never been seen. A prediction so certain that no physicist doubts it and so remote that no observer will ever confirm it. The universe knows what a black dwarf is. It knows how to make one. It's been working on it for 13.8 billion years, and it's not even close to being done. So tonight, when you look up at the stars, remember this. Every star you see is temporary. Every point of light in that sky will one day go out. Some will explode, some will collapse. But most, the quiet majority, the sun-like stars that make up the bulk of the galaxy's population, will end their lives as white dwarfs, and those white dwarfs will cool. Slowly, patiently, relentlessly. Across timescales so vast they make the age of the universe feel like an afternoon. They will cool until there is nothing left to radiate, until the glow finally stops, until the last photon escapes and there is only darkness. And what remains after all of that? The cold, dark, dense, crystalline remnant of something that once burned bright enough to warm a planet and sustain life for billions of years. That is a black dwarf, the universe's most patient creation. An object that exists only in the mathematics of physics and the far future of time. An object that every white dwarf is slowly, inevitably becoming. An object that none of them have become yet. Because the universe, old as it is still too young. And the stars, dead as they are still too warm. And the light, faint as it is still shining. Still crossing the darkness. Still refusing, for now, to go out.